Okay, well, let's get to it then. So we're talking about symmetries, and we saw last time that abelian symmetries or subgroups of non-abelian or abelian subgroups of symmetries like the rotation group, SO3. If you take SO3 and look at, say, rotations around just a particular axis, then those are, of course, abelian because you just have a single angle parameterizing that rotation, and you can rotate in whatever order you want. So that's an abelian subgroup. And we saw that those abelian subgroups by Stone's theorem have an associated Hermitian operator. So let's see how that Hermitian operator then is related to conservation laws. So that's what we'll be talking about. And something you'll derive, I guess, on the homework, or maybe we've seen it before, but it's easy enough to remember that if you have an operator, A, then the change of the expectation value of the operator with respect to some state that's evolving under the Schrodinger equation, that expectation value obeys the following equation of motion. You can just derive this from the Schrodinger equation. So we have that. And so what it means is that if the Hamiltonian commutes with the operator, and the operator itself is time independent, then this expectation value is a constant. Is a conserved quantity, right? It's a constant. It's a constant of motion, if you want. So for instance, the Hamiltonian itself, of course, commutes with itself. So the expectation value of the Hamiltonian, which is the energy, well, it's the average energy. It is a constant of the motion. So energy is conserved, so it's a conserved quantity. But that's true for any operator that commutes with the Hamiltonian. So we can look at some examples. We can look at spatial translations, for instance. And what spatial translations will tell you is if you take the expectation value of the Hamiltonian and say you look at translations by an amount A, then of course we know what the translated kets look like. Those are just the, by Stone's theorem, the exponentiated momentum. Well, sorry, let's note A here. It's the original state translated by A, so this is the translation operator according to Stone's theorem, the unitary associated with translations. And over here we have right, that's what it is. And if we have a if these translations are symmetry, if our system is translationally invariant, then this better be equal to the expectation value of the non-translated states, right? Because if it's a symmetry, then the translation shouldn't do anything to the expectation value. And so using the Stone's theorem, you can actually now derive commutation relations. And we'll see it comes up again and again, where we have these exponentiated Hermitian operators like a momentum or an angular momentum. And what we'll be able to do is Taylor expand around small a small value of the group parameter. It could be a small angle, could be a small translation, whatever your parameter is that describes your group elements. For rotations around an n hat, we will be able to expand around small theta, for instance. And that's a general property of Lie groups. Things that have a continuous set of group elements like rotations. Those are, generally the ones in physics that we worry about. They're called Lie groups. And for those, you'll always have these abelian subgroups, which can be written, the group representations, the unitaries, can be written as exponentiated Hermitian operators. And it's always the case that you can expand those around the identity, and you'll be able to get the associated Lie algebra, as it's called. Well, I'll show you that for these translations. So what do we have here? We have that H has to be equal to all this stuff. And if we expand around small a, what we would get is, so when a is equal to 0 here, the exponentials vanish, so you just get H. And then you get, from this exponential, you get I over H bar P dot A times H. And then from this one, you get minus H I over H bar, and now the P is over here. Remember, the P and the H don't necessarily commute, but you see that they will, because what we learn here is after we cancel these H's on both sides, what we learn is that we must have that A dotted into this commutation. So it's the momentum along the A direction that has to commute with the Hamiltonian. If A is arbitrary, if this expectation value is invariant under arbitrary translations, then of course we could conclude that H commutes with the momentum at any direction. So it means then we can conclude from this, which this is, by the way, called Ehrenfest's theorem. We can conclude from Ehrenfest's theorem that P does not change in time. So it's conserved. So you see symmetries lead immediately via the Ehrenfest's theorem to conservation laws, meaning you can, if you have a symmetry and you identify some abelian subgroup, or if your symmetry is abelian anyway, like a translation, then what you get from that, from Stone's theorem right away, is an observable. And you can show that this observable has to have a constant expectation value. So it doesn't change in time, so it's a conserved quantity. And this is sort of the classical analog of, having conserved energy, conserved momentum, whatever have you. You see each one of those conservation laws is associated with a symmetry. This is a little bit like Noether's theorem, which you might learn about in some other classes.
Wait, I might have missed something because I just had to step out. You said that in the A, of course, e to the power of 0, of course, that just 1, and then that becomes H. But so you're saying that other A, though, I over H bar, and then the P dotted with A. What was the value of A then again? Could you just, what was that again? Because
that's the amount you translate. We're looking at a translation of X by an amount A. It's arbitrary. And what we're saying is, if if your system is invariant under translations, meaning that, you know, you can move your x coordinate around, shift it around by an arbitrary a,
Mhm.
or, you know, in 3 dimensions, just move everything by some amount, then your expectation values shouldn't depend on whether or not you shift your state by that amount. So then this must be true. And that means immediately from that, you can expand around small a and get a commutation relation between the Hamiltonian and the momentum.
I see. Okay, that makes more sense now. Okay, I think that's good.
And that's a general rule for groups that, you know, have a continuous set of group elements. So like rotations or translations, we'll always be able to identify like an abelian subgroup, like a rotation about an axis or something like that, or just a translation. And we'll be able to expand the unitary around the identity. So all that stuff, we've done this before, you know, expanding this kind of thing. We've done this over and over again in this class, but in this portion of the class, we'll see that such an expansion leads you immediately to the concept of Lie algebras. So the algebras associated with groups of symmetries, like the rotations. For the rotations SL3, there's an associated algebra of the associated observables, which are, of course, the components of the angular momentum. So that's kind of where we're going. And you'll see that the algebra is, you know, associated with the relationship between rotation matrices.
And you said it was related to no, you mentioned Noether's theorem, right?
Noether's theorem, yeah.
Yeah. All right, good. Okay, thank you.
It's similar, but this is different. This is kind of that theorem. I guess you might see it in field theory, but it's more of like a classical theorem of field theories. So it's not. It's a little bit different, but
Yeah, I don't, he mentioned it. We had looked it over in our classical mechanics class, and we're taking the grad.
yeah, you might have done it in classical mechanics, yeah. But it's the same kind of idea, is that whenever you have a symmetry, that is associated with a conserved quantity. Now in the Noether's theorem, it's current, I guess, but here you have a symmetry and it's associated by Stone's theorem with a Hermitian operator, which is an observable. And that observable will have a constant expectation value. So its expectation value will be a constant of motion for your system. So a symmetry is related to a constant of motion here. That's pretty powerful.
Yeah, sure.
So, okay, now we can go back to rotations. And we will consider now rotations about an axis. And we know, so you pick an axis, n hat, and we're going to rotate by some angle theta. And we know, again, this is an abelian subgroup of the rotation group. So it means that we have Stone's theorem. So we can think about the rotation operator associated with that. So we could label it with the axis, and it's going to go through some angle theta, and we know we can write it as e to the minus I theta, some Hermitian, some vector of Hermitian operators dotted into n hat. That's by Stone's theorem. And now we're going to try to see what these observables are. We know it'll be the angular momentum, but we're going to try to understand something about it. So how do we do that is we go back to the rotations themselves and see what rotations even do, like say to a vector. So suppose we set up a coordinate system, X, Y, and Z. And then suppose we have our n hat direction. And let's say we have a little vector that we're going to rotate around. So we have a vector. You know, we're going to rotate it around this axis. All right. And we're going to take it and rotate it around to some V prime. And suppose that's, you know, by an angle theta here. All right, so we're kind of taking this V and rotating it by an angle theta around this n hat axis. And you know, you can sort of figure out which way it has to go by the right-hand rule or something. Stick your thumb along n hat and your fingers curl, you know, which way the positive theta direction will be. So you can actually figure out what V prime is here in terms of V. V prime should be, well, first of all, there'll be some component of V prime along n hat itself. So, and we don't know what that is, but let's say it has some magnitude alpha. We don't know what it is, but it'll have some component along n hat itself. And then we know that if you rotate by an angle theta away from the original position of the vector V, then we know that the component along the V direction must just be cosine theta V. And now there will be a third, it's a vector in 3D, so there should be some third orthogonal, there should be some other direction, and which V has a component, and that's the one that's kind of out of the plane here, that's formed by n hat and V. So V and n hat, they'll form a plane. And then we know that V prime is kind of out here, out of the plane. That makes sense. It's sort of hard to see, but you have n hat and a V, and then if you rotate V to V prime, then V prime will have a component that's perpendicular to the plane formed by n hat and V. So there's a third component that's mutually perpendicular to both n hat and V, and so that should have a magnitude sign. And we can actually figure out what alpha is by just taking into account the fact that if you rotate a vector, then its magnitude stays the same. It's just a rotation. So we can actually take this and calculate the magnitude. And what we would get, of course, is alpha squared. That comes from this part. Then we have plus cosine squared theta, and now the magnitude of V squared. That's from this part. And then we'll have some cross terms. So there will be a cross term between this guy and this guy. So there will be a 2 alpha cosine theta n hat dotted into V. And this guy is mutually perpendicular to V and n hat. So if you dot it, this guy into this, then you know that just gives you 0. So you just have this term squared. So you have sine squared theta. Then you have, if you take the magnitude squared of a cross product, you would get the following, V squared, and this 1 minus, this is just some vector identities. 1 minus n hat dot V hat, the direction along V. squared. So that's what you get.
I have a question.
Yeah.
Could you explain where, I understand you said theta was between V and V prime. Is that right?
No, not quite. So this is a rotation by an amount theta. The actual angle between V and V prime could be something else, right? Just because you rotate something by an amount theta along some axis, it doesn't mean that the angle between those two things is theta, right? It could be a different angle.
Could it be like,
In fact,
could you use phi for that instead, or like instead of theta? Wouldn't that be, because are you kind of like doing a rotation like in that plane? Is that what you're saying? Or are you just doing a single rotation?
So this is a 3-dimensional, first of all.
yeah, it's 3-dimensional, that's right.
So then when you say that one component of V prime is V cosine theta,
Yes.
that's why I'm asking.
Well, no, but just because this is cosine theta, the angle between two vectors, if you take the two vectors and dot them into each other, that's equal to the cosine of the angle between them, which
Yes.
I'll call phi. But if I take this and dot it, if I take V prime and dot it into V, I don't get cosine theta. I get something complicated. I get alpha times, n hat dotted into V plus, I mean, this part is cosine theta, but there's other stuff, right? There's just other stuff going on. So it's not, theta is the angle by which you rotate something.
That's, I follow, but my question is, when you said V prime is equal to alpha n hat plus cosine theta V,
Yes.
that's the component I would like to, where's that coming from? That's what I want to know.
Oh,
Does that make
it's,
sense?
yeah, well, it comes from the the kind of trig associated with having a rotation by an amount theta here. So
Okay.
if you project
Mm-hmm.
if you project this vector V prime onto V, then that piece of it will be a cosine theta.
Okay. Okay.
So
that's the trig identity I wanted. Okay.
Yeah. I used to assign the full trig thing as a homework problem, but maybe I'll do it in recitation next week.
Sounds good.
All of the trig identities for this. Yeah. But okay, but in general then, if you buy that the trig identity tells you that this component is cosine theta, then this is the general form. And the point is, I just don't know what alpha is. Maybe if I was really good at trig, I would tell you right away what alpha is. But I don't. All I can tell you is this is cosine theta, this is sine theta. And now I'm just trying to figure out what alpha is by setting the magnitude of V prime squared equal to the magnitude of V.
Okay.
And so if you do that, then the only solution for alpha is actually it's 1 minus cosine theta n hat dot b. And you can tell if you substitute this guy into here, you'll get just the right thing that you need in order for this cosine squared theta to combine with a sine squared theta and give you just 1. You can sort of so again, I might do that algebra, this in recitation, but you can just solve this equation. And what you'll get is that alpha is equal to this. So in the end, how is V prime related to V and n hat and all that? Well, it's 1 minus cosine theta, and it's n hat dot V. This is the portion along the n hat direction. Then there's a cosine theta V, and then there's a sine theta n hat cross V. So it's a decomposition of the rotated vector into components that are along the original vector, a component that's along the axis that you're rotating, and then the mutually perpendicular direction. That's all we're doing there. It's just a little bit of tedious trig, so I don't want to spend too much time on it, but I can, for a full derivation of this, I will do that in recitation next week, if you're interested. It's not really quantum mechanics, so I don't really feel like doing it right now. Also,
Yeah.
I'll probably screw it up, but it's just some trig. Okay, but what's the point of this? The point of this is that this is what a rotation matrix does, right? If you have a vector V and you rotate it by an amount theta, then whatever this is doing, which is transforming V to V prime, that's, we should be able to take this, right, and write it as V prime is equal to some matrix now, which I'll call n hat theta is some matrix, some 3x3 matrix, right? That takes components of V and rotates them in this way. And why did we write it out in this funny way with all these components? Is because now we can do the thing that I wanted to do, right, that I did already for the translations, right? I can expand around a small angle to get the equivalent of a commutation relation, but for these rotation matrices. So I can now expand around small theta. And if I do that, then, well, small theta here, this would give me 1 minus 1, this is 0, this will be 1, and the sine theta will be approximately theta. And that's the leading order term in theta, because the higher order terms here are going to be theta squared from the cosine, from the Taylor series of the cosine. So if you expand around small v, what you would get then is that v prime is equal to v plus theta n hat cross v. So you see there's the identity, that's the rotation not doing anything, plus something that's proportional to theta. It's quite similar to the translations that we did. See, when you expanded around small translations, you got the identity plus something that's linear in the group parameter. In this case, the translation here, it's an angle by which you're rotating. The same idea. Except now you got this complicated cross product here. But that's not bad because we know how that cross product works, right? We can write that as a matrix, right? We can now identify this as, T dot n hat acting on V. And because remember that we're connecting this now, this transformation back to this exponentiated thing, right? That we should get according to Stone's theorem. These guys should behave just like the rotation matrices. So if we expand this around the identity, then what do we get, right? We get that this is the identity minus I theta, T dot n hat. That's what it should be. And so if I compare this to what I actually get when I rotate a vector, which is V plus theta times something, well, you see it's quite similar. We got the theta, right? We got the identity. And so this cross product must be whatever this t dot n thing is doing. That's what it must be doing, must be taking a cross product. So, I forgot the identity. So this is equal to the identity, or 1 here, minus I, this guy, like that. Just from what it should be based on the Stone's theorem. So, okay, if you make that identification, then you conclude that t dot n hat acting on a vector should give you I, and I'll just write out the components. Right, it should give me that because that's how the cross product works. If I think about the x component of the cross product, it should be minus nz vy plus ny vz. Similarly, so the cross product is always perpendicular to the component of interest, so that's why there's zeros on the diagonal. But this is just writing out in terms of matrix multiplication what n hat cross v should be. That's all this is. If you just remember back to how cross products work between vectors, these are the components. So like the z component of the cross product here should be nx times vy minus vx times ny, so on. So we just wrote it out as a matrix vector multiplication. And moreover, we know that, well, this part, this guy right here, this should be, t hat dot n. So that means we can identify, and this should be whatever the x component of t, the x component of that t vector times nx plus ty and y plus tz and z. And so we can extract, we know where the nz's are, and we know where the ny's are, and we know where the nx's are, right? So we can actually just extract what the tx, ty, tz's are. Remember, what t is a vector of operators, of 3x3 matrices. And we know what they are now, right? We can just extract them. It's tx should be, let's just look at where the x's are. There's a here, and here. So, and it's multiplied by I. So it's 0, 0, 0, 0, 0 minus I, 0, I, 0. And ty is these guys on the corners here multiplied by I here, 0, 0, I, 0, 0, minus I, 0, 0. And tz is 0 minus I, 0, I, 0, 0, 0, 0, 0. So those are the T matrices. So let's again recap what we did. We're not doing quantum mechanics. We're just recognizing that by Wigner's theorem, right, each rotation group element should be associated with a unitary. And so the properties of those unitary operators should be just like rotation matrices. So in particular, there's something like Stone's theorem for the rotation matrices too. So there should be, whenever we rotate a vector, right? We should be able to write that as some rotation matrix times the vector that we're rotating right here. And by that Wigner theorem analogy, we should be able to write this rotation matrix as an exponentiated matrix of these t dot n hats, where t is just some other matrix, some other 3x3 matrix. And that's what we're trying to find, is those 3x3 matrices. Okay. And how are we going to find them? Well, what we do is we recognize we can expand around small angles. And in that case, our rotation matrix has to have this form where it's the identity minus I theta times this t dot n hat thing. And so then we can compare, and we actually just do a rotation and see what that does to our vector. And we can just compare that to what we should get, you know, if we interpret it as a rotation matrix of this form, right? And that's what we did. We just, this is what it looks like, a rotation looks like at small angle theta. And so this t dot n hat must be related to this cross product. And that's how we identify what this matrix is. But it's just for rotations. But you see, the point is that how these rotations work, their algebra of the rotation matrices themselves, it'll be the same algebra as the rotation group representation, which is going to be the unitaries that act on a quantum mechanical Hilbert space. So that's the connection. So you have these generators of the rotation group. And so you see any rotation matrix around n hat, we could write it now as, you know, this exponentiated thing. Yet, you know, it's any rotation we can write as I times, you know, again, as this guy. So it's minus I theta. Let me write it out completely, minus I theta, and then it's, you know, tx nx plus ty ny plus tz nz, right? Any rotation around an n hat, the 3x3 matrix associated with that rotation is given by this, where these are the generators, as they're called, and this is the axis around which you're rotating, and theta is the amount you're rotating. You can literally plug those in and exponentiate it, do the whole Taylor series thing, and you can do the thing that we did in on the midterm, I guess. You know, you can expand this exponential and figure out all the sines and cosines, you know, that you get, and so you get, in the end, you'll get a, you know, 3x3 matrix with the right entries with the sine thetas and so on. So that's what we're doing. And moreover, you can show that these matrix, these generators, as they're called, they obey some commutation relations. Particular, if you take two of them, Ti, Tj, where, you know, Ij runs from X to Z, then this is equal to I times sum over K of epsilon ijk tk. And if you remember, this is the same commutation relation as the Pauli matrices. And why is that? Well, it should be no coincidence to you anymore, because you know that spin 1/2 is a representation of the rotation group. So the unitaries that we have that rotate spin 1/2 particles that you can write in terms of the Pauli matrices that, you know, are generated by the Pauli matrices, those things should obey the same algebra as the rotation matrices. So they should have the same commutation relations. So it might seem kind of shocking that, you know, we're doing these 3x3 rotation matrices and all of a sudden we get the same commutation relations as the Pauli matrices, which were 2x2 complex matrices, but it's not really surprising at all, because a spin 1/2 was just a representation of the rotation group. So hopefully you see how these things are all kind of connected. Any questions about that?
No, I think that was pretty helpful. You showing us the above, how to do TX, TY, and TZ. But, you're saying that in actuality that if we were to expand that out, you're saying we would get a matrix with all the right sines and cosines. That's what you're saying right here. And we have the value of TX and X from above, and we have the negative I theta, and then we just expand it out. That's what you're saying. We get the right for the matrix above it. Or where you said poly matrices, you said equals, you said sine theta, so forth. Is that what you're saying? Right
I'm
here.
saying if you write down the 3x3 matrix associated with rotation by an amount theta along the direction n hat, you'll get some 3x3 matrix with an x and y and then z and sines and cosines of theta. And that matrix will be equal to this exponentiated thing. It will be equal to this.
Okay. That's
But we got here in a kind of a roundabout way. What we did is we assumed, because we have Stone's theorem, that you should be able to write down, since rotation around a particular axis is an abelian subgroup of the rotation group, we should be able to write it. It should look like this. And we're just trying to figure out what this is. And how we do that is by looking at small theta. See, looking at small theta, because it's a Lie group, it's a continuous group, you can sort of get its properties, or most of them anyway, by looking at just expansions around the identity. It's sort of like, it's quite analogous to the idea that if you have some function f of x, you can actually get all of the properties of the function by Taylor expanding around x equals 0.
Yeah.
Right. As you take more and more terms in the expansion, you get more and more of the function, right? If you've ever seen that, like a Taylor expansion of some complicated function, the first term gives you maybe some kind of line through here. Second term gives you this curve, and then as you take more and more terms, it starts filling out the function.
Yep.
Everywhere. Well, it's quite similar here. We're going to get the full 3x3 rotation matrix by just analyzing what happens at small theta and figuring out what these generators are, these t dot n hat things are.
Oh, okay. That makes sense.
And we figure them out. They're right here. And so then we know that when we exponentiate the whole thing, and now not only look at small theta, but any theta, that'll give us the right thing. And you can check that by doing the kind of, Taylor series expansion of the exponential that you did before for like the midterm.
Yeah. Okay.
Okay. All right. Any more questions? Okay, good. So.
Oh, yeah. Before you go on, sorry to interrupt you again. But you're going to go over the derivation, though, of the trig you said next recitation, so we can watch it or join, right?
Yeah, I'll go over the derivation of this.
Yeah. Okay. I mean, I you can probably see it, and if you go to basic trig and plus, usually we have, those like Sham's outline, which gives you the basic, answers to those, the tables and formulas. So, but it's always good to be able to do it again.
Yeah, this is just the trig associated with rotation. But by this angle, but
it would probably be nice if you could go over it though, just to give you an idea is like within Mathematica.
I'll do that. Yeah.
Could you go back to the image of the vector diagram you drew with n hat and v?
Yeah.
So you said v prime is equal to the r and theta v. So that's
v prime is this.
Right at the very bottom. Like if you scroll down when you did the whole, that one, the one in blue,
This.
the one in blue below that. Yeah.
Oh, yeah. Okay.
So that's basically what happens when you rotate is what that's describing. Is that right?
Yeah, so a rotation, right, in 3D is given by a 3x3 matrix that you can act with on a vector, and then you get some new vector that's rotated.
What is, okay. Okay.
And we're just trying to figure out what the form of this R is. And with guidance from Stone's theorem, but it doesn't have to be guidance from Stone's theorem. You could just also know that a rotation matrix can be written as an exponentiated matrix of minus I theta times this vector of matrices dotted into n hat, the direction along which you're rotating. And now we're just trying to figure out what the t dot n is. And we do that by doing the trig associated with the rotation.
And n hat is represents the direction.
N hat is just the direction along which we're rotating. You take n hat and we're rotating around that.
All right, that was actually my question. Great, thank you.
Yeah, you take some arbitrary vector, we pick a direction along which we want to rotate, and then you rotate by an amount theta. And we know that's given by a 3x3 matrix that acts on the vector.
Yeah.
And we also know that that matrix should have this form.
Mm-hmm.
And now we're just trying to figure out what this form, what the t dot n is. Like, what are those things? There should be some other 3x3 matrix. What is it? Well, you can figure it out by looking at small angles, rotations around small angles, because then your 3x3 matrix reduces the identity minus a linear term, and that you can extract from the Taylor series what t dot n is, and that's what we're doing with this trick.
Cool. That's great. Thank you. Because by the time you finished all of that, I lost track of what n hat was, but that's good. Thank you.
Yeah. All right, so that's the rotations. And what does it mean? Well, it means that when we have a representation of the rotations, now we do a representation of SO3. Again, what's the representation? It's every element in the rotation group, like one of these 3x3 rotation matrices, can be associated with a unitary that acts on a Hilbert space. And so this unitary, which will depend on theta, and of course it'll also depend on n hat, so we can add an n hat to it. What is that? Well, that, again, by Stone's theorem now, the real Stone's theorem, not just like a kind of a half, you know, a sort of halfway. Stone's theorem will tell you something about rotations. Now, the real Stone's theorem tells you that this should be equal to minus I theta j dot n hat over h bar. And now this thing must behave just like these R's do. So this commutation relation that these T operators obey, those must be the same commutation relations that J obeys, with J being the angular momentum. So it must be the case that, you know, the components of angular momentum and of course now there's this extra h bar floating around, whereas before we had just no h bar. So if you correct for that h bar, then these commutation relations become I h bar sum over k epsilon I j k jk. And these are the commutation relations for angular momentum. Any angular momentum, orbital angular momentum, spin 1/2 angular momentum, they have to obey those commutation relations. So remember that the spin angular momentum for spin 1/2 is, you know, h bar over 2 vector Pauli matrices. So there you go. That's why the Pauli matrices obey those commutation relations. They don't come out of nowhere. They're actually fundamentally tied to properties of rotations in 3D space. Because why? Again, because spin 1/2, spin 1, or angular momentum in general, that's the observable associated with the unitary that performs a rotation. And the unitary is a representation of the rotation group. And the rotation group itself is, of course, SO3. It's the set of rotation matrices, 3x3 rotation matrices. But these unitaries, they act on a Hilbert space. They don't have to be 3x3. They could be 2x2 for spin 1/2. For spin 1, they are 3x3, but you can have spin like 3/2, and then they would be 4x4. So, but even though that's true, they all will obey this commutation relation, because that just comes from the algebra of the Lie algebra associated with the rotation group. So hopefully that is starting to make sense.
Wait, did you say that the unitary can be any 2x2 or 3x3 matrix, but not the rotation matrix? Is that a distinction you made, or did I mishear that?
Well, the unitary will be a representation of the rotation group, and it'll act on some Hilbert space. Now, you tell me what Hilbert space it is, and then I can sort of tell you what the unitary is. Like, that's the spin 1/2 Hilbert space. Remember, that had two states, right?
Mm-hmm.
Spin up and down. So the unitary is going to be some 2x2 matrix.
Okay, because it's a two-dimensional.
Yeah, and we already know what those matrices are. Those are the D1/2 things.
Mm-hmm.
But for other spins, they'll have more dimensions. So they're not related to each other. It's important. I think people often get confused what the 3x3 of the rotation matrices has to do with the unitary, and the answer is nothing other than the algebraic properties that the 3x3 matrices have, the commutation relations. But other than that, they don't have to be related at all. They just have to have the same relationship, regarding the group, the rotation group. And so that has to do with, the rotations themselves by the angles. It doesn't have anything to do with, like, the dimension of the Hilbert space or something. That's an independent thing.
Yeah, I understand. Got it.
Okay, great. So as soon as you have these unitaries, right, those now are the way rotations act on that Hilbert space, whatever it is, spin 1/2, spin 3/2, whatever, some Hilbert space. That's what rotations do to states in there. And so that allows us to define concepts like scalars, vectors, and tensors, because classically, I don't know if in classical mechanics, you probably talk about this, right? You talk about, like, what's a scalar, what's a vector, what's a tensor, and or maybe you've taken GR or something. And classically, those things always mean how do those objects transform under rotations? Do they rotate around like a vector? So then that's a vector. Or do they not rotate, and that's a scalar? Or to do something else more complicated, then it could be a tensor. So there's some transformation rules under rotations, right, that objects obey, that define whether or not they're a scalar, a vector, or a tensor. So in quantum mechanics, of course, we don't have quantities in and of themselves. We have operators, Hermitian operators, right, that represent observables. And so the concept of scalar, vector, and tensor has to be extended to Hermitian operators. But it's easy to do because we have the unitaries available to us, so we know what the rotations do. So for instance, what would a scalar operator be? Call it S. What should it do? Well, under pretty solid grounds, what it should do is its expectation value, right, shouldn't change under rotations. So if we rotate the ket here, that we're taking the expectation value of, which we can also write as phi u dagger now associated with that rotation, and r here is some rotation. It's like an n hat and a theta, some choice of n hat and theta. It's just shorthand notation for that. Then this, should be equal to this, right? That's what a scalar is. It's some observable that when we measure it, it doesn't change if we rotate around our coordinate system. So scalar operator is one which satisfies u dagger su is equal to s. Satisfies this. Anything that satisfies that is going to be a scalar. What is it? A scalar operator. It's an observable, a Hermitian operator associated with, a classical scalar quantity. So that if we take the expectation value, which would be the average measurement, then that doesn't change under rotations. Okay. And if you wanted, you could now stick in the exponentiated u here, right? We can stick in this guy right here. You would get, plus, e I theta over h bar, j dot n hat, you get s, and then e to the minus I theta over h bar, j dot n hat. That's equal to s. You can now expand around, small theta, and what you would find is that j dot n hat commutes with s. Right, it's pretty easy to see. It's the same calculation we did before for the for these t guys. No, maybe I got rid of it, but it's the same thing. So you just Taylor expand around small theta, and you'll get this equation just becomes this. Okay, so that's scalars. But what about vectors? Vectors are different. If you rotate your coordinate system, well, the vector will rotate also. So that transformation law looks like the following. So we have a vector operator, v, and it's a vector, so it should have 3 components, x, y, z. Then what it should obey is that if we rotate our state around, then what should happen is that expectation value should rotate like a vector would rotate. So it should be a matrix multiplication, right, of, and these are now the 3x3 rotation matrices, right, of the rotated components of that thing. So you see, it's different now. If it's a vector operator, then it'll have 3 components, and those components will rotate just like a vector in 3D would, even though the operator itself might have some other dimension. Hopefully that makes sense. This is a property of how the operator changes under rotations. There's nothing to do with the actual space on which that operator is acting. That's a different thing. So, and then if we write this out, right, if we write it out in terms of if we substitute in for u, we substitute in our Stone's theorem thing for u, then what you would get is e to the I over h bar theta j dot n hat v sub I over h bar theta sub n hat, that should be equal to sum over j r ij v j. And again, this is the 3x3, rotation matrix that we were looking at before. This is that, this guy. So a vector operator will satisfy that. And that allows us to, this relationship allows us to then derive commutation relations between what? Between any vector operator and the j's, because we can expand around small theta again. And how do we do that? Well, it's easy. We already know how to expand this side because we just did that with those T matrices. So what we do is we say, well, if this is equal to v prime I, then the vector v prime must be equal to the vector v plus theta. And now let's, instead of n hat, we'll choose just for convenience for now, we'll choose n hat is equal to x hat. So we'll rotate around the x direction. So that's x hat cross v. And if you write out what the components are, it would be vx and then vy minus theta vz and vz plus theta vy, like that. So that's this side of it. And the left-hand side, this guy, right? Well, we know what that is too, because we can do the Taylor series. It's the identity plus I over h bar theta jx. And then here it's vi, whichever one of those components. And here we'll have I minus over h bar. Ugh. Theta jx. Okay, and whatever those components are, that's of course equal to this vx vy minus theta vz minus or plus theta vy. So that's the equation, and now we can look at the individual components. For instance, for the y component, for this guy, if we expand, we take this to linear order in theta, we would get that, right, if this is vy, then this is equal to vy minus theta vz. And we conclude from that I, and this vy will cancel the identity piece of this. And what you'll find is that there's a commutation relation between the vector of angular momenta and any arbitrary vector operator. That's equal to minus h bar vz. And you can keep going, and what you'll find if you do all the components, so this is the y component. If you do all the components, you'll get a general set of commutation relations, which is that we can bring the I over to the other side, which is ji v j is equal to I h bar sum over k epsilon I j k v k. So those are the commutation relations satisfied by vector operators. And it's no surprise that it's the same as the relationship between angular momentum components, because angular momentum itself is a vector. So it should be the same thing. But here we derived it, from kind of first principles, just by considering what rotations should do to an expectation value of an observable that corresponds to, a vector. any observable like that must satisfy this set of commutation relations. What we're going to do now is study these commutation relations in detail for the angular momentum. The implied sum over k here. And what we're going to do is we're going to recognize that this operator, we take j and dot it into j, which would be, jx squared plus jy squared plus jz squared. This is a scalar, as it should be if you dot two vectors into themselves. That should rotate like a scalar. It shouldn't change. Magnitude of the vector shouldn't change under rotations. And so we'll be using that. And in particular, we'll also use the fact that the scalar operator should commute then, and I'll call it, j squared, should commute with all the components of the angular momentum. And so what we'll be able to do is find eigenstates of both a component of angular momentum, like along the z direction, and this guy. We'll be able to find simultaneous eigenvalues, eigenvectors of both of these operators. And that's where we'll start, I think, next time, is exploring that in detail and finding what the eigenstates are of angular momentum. So that's, and then we'll figure out how to add angular momenta together.